Hello. Um, Man, it's been an exciting day so far in terms of animals. I uh, There's another cat in the backyard, and Ivan the cat is interacting with him. It's kind of funny. I just went out into the backyard during passing period, and they were both just maybe 10 feet apart, just staring at each other. And then the other cat saw me and ran away, and then Ivan chased him. It's very cute. It's like they're trying to play with each other, but they don't know how. Um, okay, so I am gonna get started because this is kind of a long lesson, and I'm going on a run right after this. So I'm. Oh, that's the side that's. So I got my headband on. I've got my sunscreen applied. I'm ready to go right when this class ends. So what we're going to talk about today, first of all, is the intuitive meaning of Gauss's law. And just to remind you, Gauss's law says that the flux of the electric field through some surface is equal to the charge enclosed by that surface divided by epsilon naught. Okay, so the name of this surface, when we're talking about Gauss's law, is often called a Gaussian surface. So you will hear me use that term over and over today. So sort of if we want to understand what Gauss's law is saying, we have to know what sort of the intuitive meaning of flux. And so it turns out that flux is basically what it's doing is it's counting the number of field lines crossing the surface. And it's doing that, with signs. So when I say that, so for example, what if I have a Gaussian surface? Okay. And what if the electric field line comes up and it leaves the surface? So we have an electric field line that goes, and then maybe later on it comes back into the surface like that. Like that. So when it's going out, it would contribute positively to the flux, and when it's going back in, it would contribute negative. So there's no net flux from this electric field line. So what I'm going to do is I'm going to draw an electric field line pattern. All right, so what if we have a +1 charge? And I'm going to let +1 have 8 field lines. 1, 2, 3, 4, 5, 6, 7, 8, like that. And all these field lines are going outwards. Now, what if I had a Gaussian surface that surrounded this charge? So in other words, I have a Gaussian surface that is enclosing the charge. And it doesn't matter what the shape is as long as it's enclosing. So I'm going to call that S1. So what we can see is we're just going to count how many lines are passing through the surface. So, and we're going to do that with the sign. So in other words, if it's going in, it's negative. If it's going out, it's positive. So all these field lines are going out of the surface. So I have 1, 2, 3, 4, 5, 6, 7, 8. So that means the flux through surface 1 is plus 8. Okay? And it doesn't mean that it's plus 8. It means it's proportional to 8. All right? So that's why I say approximately, because it's not exactly equal to the number of it. It's proportional to the number of field lines crossing the surface. And you could check for yourself that if you change the shape of the surface, so maybe I don't know, I make another surface that looks like this. As long as the surface encloses the charge, so I'll call that S2. All right. It's still, the flux through surface 2 is also 8. All right. But what if I had a surface that doesn't enclose the +1 charge? So maybe I have a surface out here like this, and that is S3. It has one field line going in, and then the same field line leaves. So this, when it goes in, it contributes a minus, and when it goes out, it contributes a plus. So the total flux through this surface is 0. Okay? So, and that is consistent with Gauss's law, because if the charge enclosed by a surface is 0, then the right-hand side is 0, which means that the left side also has to be 0. Okay? And furthermore, it doesn't matter what the shape of the surface is. As long as it encloses the charge, it has the same flux, and that's what we just saw. Now, what if we had a minus charge? Minus charges have field lines that go in. All right, and as we said, the flux if field lines are going in, the flux is negative. So if I have a Gaussian surface that surrounds this negative charge, all of these field lines contribute negatively to the flux. All right, so I have 8 lines going in. So if I call that surface 4, the flux through surface 4 is going to be minus 8. That is consistent with Gauss's law as well, because if you enclose negative charge, you get negative flux. What if we have more than one charge inside of our Gaussian surface? So maybe I have +1, and then another +1. Okay, so if you recall, the electric field pattern for this was looks something like this. All these field lines are going out because it's a positive charge. All right. So what if I had a Gaussian surface that encloses both charges? So that would be something like this. So it encloses both. And I'll call that surface 5. And so going around the boundary of that surface, I have you know, all these lines are going out. And there are 16 lines going out. All right? So that means that the flux through surface 5 is plus 16. And that is consistent with Gauss's law. Because if you enclose twice as much charge, you have twice as much flux. Okay? Now, here's where it kind of gets interesting is what if we had, you know, even though there are two charges, what if we have a Gaussian surface that only encloses one of them? So even though there are two charges, our surface only encloses one. So I'll call that surface 6. And I can see it has 1, 2, 3, 4, 5, 6, 7, 8, 9 lines going out. But you can see that this line, it goes in and out of the Gaussian surface. So this line also contributes a negative. Okay. So what we get is for surface 6 is that the flux is again plus 8. So again, even if you have multiple charges present, more than one charge present, if the surface only encloses one of the charges, you still get the flux of a single charge. Let's see how this works. Let's see how this works for a dipole situation where we have a positive and a negative charge side by side. Okay, so there is a dipole electric field pattern. It looks like Manifold's plane. So what if I drew a surface that encloses both of these charges? Okay, so I'll call that surface 7. All right, what we get is I can see this line is going out, so that contributes a plus. This line is going out, so that contributes a plus. The line goes out, but then it curves back in, so it makes a minus. This line is going in, so that makes a minus. This line is going in, so that makes a minus. And this line is going out, so that makes a plus. So I have 3 outward lines and 3 inward lines. So the total amount of flux through surface 7 is 0. Okay? So basically what I'm trying to say, all right, is that what I'm trying to say is that Gauss's law is a restatement of the rules for electric field lines. So if you recall, so that is the intuitive meaning of Gauss's law. And just to recall the rules for electric field lines, if you have a positive charge, the field lines go out. If you have a negative charge, the field lines go in. If you have twice the amount of charge, you have twice the amount of lines. So if you are obeying the rules for electric field lines, then you automatically have Gauss's law. Okay. And this surface, of course, encloses no net charge. It encloses a positive and a negative. All right. So we can actually use Gauss's law plus symmetry to calculate the value of the electric field. Okay, so I want to take a moment to talk about different types of symmetry that we encounter. Okay, so one type of symmetry is called spherical symmetry. All right. So spherical symmetry means that, let me just grab something. Give me a second. So here's a tennis ball, and if you take a tennis ball and you rotate it, and let's imagine that this is just a perfect sphere, so it doesn't have any markings on it, because the tennis ball has markings on it, you can tell what orientation it's in. But if this had no markings on it, you would have no way of knowing which way it is if I rotate it around. Okay? So that's what spherical symmetry is. It means you can rotate it and it's still a ball. Okay? So if you have spherical symmetry, all right, what that means, so like a point, for example, so if you have a spherically symmetric charge distribution, the electric field has to point outward. So the electric field points radially outward. All right? Now, and the reason for that is that the electric field always has the same symmetry as the charge distribution. So if the charge distribution is spherically symmetrical, okay, then that means that the electric field also has has to be spherically symmetrical, because if you take the charge distribution and you rotate it, it's still the same charge distribution, so why would the electric field change? Okay, so it has to point directly away from the center of that distribution. And furthermore, it can only depend on distance from the center. All right? It can't depend on latitude and longitude. Why? Because if it's spherically symmetrical, every latitude and longitude is the same. All right? This tennis ball technically isn't spherically symmetrical because, this latitude and longitude is over the P and this latitude and longitude is over the N. So, you could tell where you are because it has markings on it. But if you had something that was truly perfectly spherically symmetrical, the only thing that can change is the distance from the center. Okay? So when you have spherical symmetry, okay, your Gaussian surface should be a sphere. And so we would take our Gaussian surface and we would put it at put the center of the Gaussian sphere at the center of the charge distribution. Okay? So that's if you have spherical symmetry. The other type of symmetry we will encounter is cylindrical. Okay? So a good example of a system with cylindrical symmetry is an infinite line of charge. Okay? Why is an infinite line of charge? Why does it have cylindrical symmetry? Well, here's a cylinder. Okay? I'm just using a Coke can. And let's imagine that it's an infinitely long cylinder. Okay? If I took the can and I rotate it, it's still an infinitely long cylinder. If I take it and I move it this way or that way, assuming it's infinitely long, you still have an infinitely long cylinder. So if the charge distribution has that symmetry, then the electric field that it produces also has that symmetry. Okay? So here's our infinite line of charge. And what that means is that the electric field has to point directly away from the infinite line of charge. All right. It can't, because it's an infinite line of charge, it can't depend on if you go side to side. It can't depend on which direction you're looking at the cylinder from. This is a sort of a two-dimensional perspective, but if I was doing this in 3 dimensions, okay, the electric field pattern would be kind of like this. So it points directly away from the axis of the cylinder. All right. So in this case, the electric field points directly away from the axis of the cylinder. All right, and it only depends on distance from the cylinder, distance from the axis. All right. So in other words, the only thing that matters is how far you are away from the axis. In this case, you want your Gaussian surface to also be a cylinder. So basically the lesson is that your Gaussian surface always has the same shape as the symmetry of the object. Okay. So yeah. All right, so now we're going to use these facts to actually calculate some electric fields. So the first one I want to talk about is the electric field of a point charge. Now, we already learned what it is. We learned it. That's Coulomb's law. Okay? We learned that the electric field from a point charge is kq over r squared. But Gauss's law actually allows us to derive this. Okay? So let's suppose we had a point charge. A point charge is kind of like a tennis ball. It has spherical symmetry. We can take the point charge and rotate it. It's still a point charge. All right? So that means that the electric field points directly away from the point charge. And I'm trying to make this look kind of like 3D. Like that, points directly away. And so our Gaussian surface is going to be a sphere centered there on the point charge. The radius of the Gaussian surface, we're going to call that r. Now, Gaussian surfaces are completely imaginary. Okay, the surface is imaginary. We're imagining calculating the flux through it. So I'm imagining a Gaussian sphere centered on the point charge that has a radius r. So let's apply Gauss's law to this. The integral of E dot dA is equal to charge enclosed over epsilon naught. All right. The charge enclosed, and we should say this charge is plus Q. All right. This Gaussian sphere encloses that charge. It's called plus Q. So the right-hand side of Gauss's law is really simple. It's just plus Q over epsilon naught. All right. In the last lesson, we talked about how if you have a sphere, you can think about a sphere as a single face. So the flux through that is just going to be E dot A. But now here's where it's important that it has spherical symmetry. If it has spherical symmetry, the area vector points directly outward. And the electric field also points directly outward. So that means that our angle is between those two is 0 degrees. So that means that this dot product, remember, dot products are magnitude of first vector times magnitude of second vector times cosine of the angle between them. So now the angle between them is 0. So it's just magnitude of the first vector times magnitude of the second vector. Okay, I'm going to go sideways now. The area is the area of the Gaussian surface, which is 4 pi r squared. So I have electric field times 4 pi r squared. So I've replaced area with 4 pi r squared equals plus Q over epsilon naught. Divide both sides by 4 pi r squared. I get that the electric field is plus Q over 4 pi epsilon naught r squared. Boom. Now you might say, well, this isn't exactly the same as that. Right? They both have Q over r squared, but this one has K, and this one has 1 over 4 pi epsilon naught. What gives? Well, it turns out that 1 over 4 pi epsilon naught is equal to K. So let's try that. So this isn't showing. I'm going to hold it like this. So 4 times pi times epsilon naught. Epsilon naught was 8.85 times 10 to the minus 12. So that's 4 pi epsilon naught, but then remember it's 1 over 4 pi epsilon naught. So I'm going to take that and raise it to the negative 1. And we get 8.99, or it's 8,991,000,000, blah, blah, blah. So that is 9 times 10 to the 9th, essentially. All right, now I was rounding the value of epsilon naught. So at any rate, what we have shown here is that K is actually equal to 1 over 4 pi epsilon naught. And in fact, if you're doing more advanced physics, you don't use K at all. You just use epsilon naught. All right, so Jackson electrodynamics, for example, no mention of K. You just use 1 over 4 pi epsilon naught. So now let's apply Gauss's law to a cylindrically symmetric system. So let's talk about the electric field of an infinite line of charge. Okay. So an infinite line of charge, and it has dq dx equals lambda, and it's equal to a constant. Now, if you have an infinite line of charge and it has cylindrical symmetry, lambda has to be a constant, because if lambda didn't, if lambda did not depend on, if you take an infinite line of charge and if you shift it, you better have the same charge density once you shift it. Otherwise, it's not symmetrical when you shift it along the axis of the cylinder. So anyways, it's a constant, and if we multiply both sides by dx, we get dq equals lambda dx. Okay. So I'm going to do a side view. So here's the infinite line of charge. And we know that its electric field lines point directly outward. I'm not going to draw too many of them. And if I wanted to draw a 3D view, I'm not even going to draw the electric field lines at all because it'll get too confusing. So plus infinity, minus infinity. So if you have a cylindrically symmetric system, you want your Gaussian surface to be a cylinder. So your Gaussian surface reflects the symmetry of the charge distribution, as does the electric field. So this looks like a rectangle because if you take a cylinder and you look at it from edge on, it just looks like a rectangle. Okay? We will say that the length of the cylinder is L, and the radius is R. What does this look like from the 3D perspective? You have the cylinder is basically wrapping around the, so here's L and here is R, around the cylinder. Is it wrapping around the infinite line of charge? So let's apply Gauss's law. Gauss's law says that the integral of E dot dA, all right, the flux, is equal to charge enclosed over epsilon naught. Now, last time when we discussed a cylinder, I said that a cylinder has three faces. It has the two end caps, and then it has the middle face. So, you have 1, 2, 3. So I have, and I'm going to call it left end, right end, and middle. So the left-hand side is electric field dot area plus electric field dot area plus electric field dot area. And this is the left side, this is the right side, and this is the middle. Okay? Now here's the cool thing. For the left and the right side, the area vector points to the left or to the right. So that here the area vector points to the right. On the left side, the area vector points to the left. But the electric field points up and down. So as you can see, the angle between those two is 90 degrees. Okay? So these two both have theta equals 90 degrees. The cosine of 90 degrees is 0. So these two don't contribute, those two end caps don't contribute any flux. Okay? If I go to the middle, for the middle, the area vector points directly away perpendicular to the surface. And then the electric field also points directly away and perpendicular to the surface. So for the middle term, the angle is 0. And the cosine of 0 degrees is 1. So what we get on the for the left-hand side of Gauss's law is just EA, where A is the area of the middle face. Let's talk about the right-hand side. If you have an infinite line of charge, it's obviously going to have an infinite amount of charge. But our Gaussian cylinder is finite, so it's only enclosing a portion of that infinite cylinder. And in fact, it's enclosing a length L of the cylinder. Or of the cylinder is enclosing a length L of the infinite line of charge. Okay? So what I do is I go back to here, and what that means is that the charge enclosed is just going to be lambda times L. All right? Because the dx in this case is the length of the cylinder. So on the right-hand side of Gauss's law, I have lambda times L over epsilon. What is the area of the middle face of the cylinder? Well, the middle face of the cylinder is a circle which has a circumference 2 pi r, and it's extended down the length of the cylinder. So 2 pi r times L. So the electric field is, or area is 2 pi r L. All right. We see that the L's cancel, and then I can divide both sides by 2 pi r, and I get that the electric field is lambda over 2 pi epsilon naught r. If I replace it with k, 1 over 2 pi epsilon naught is 2k. So I could also write it as 2k lambda over r. And this is the same as the answer we got when we did the integral from negative infinity to infinity. Okay? So that's really cool. So in certain situations, Gauss's law allows you to calculate the electric field much easier than when you do it by integration. See, look at, what would you rather do? Would you rather do an integral from minus infinity to infinity, or would you like to do, 4 lines of simple algebra? Okay? So again, if the distribution of charge is highly symmetrical, then Gauss's law is the way to go. All right? We're going to do one more example, which is an infinite plane of charge. Okay, so if I were to look at an infinite plane of charge, sort of from an edge-on view, if you have a plane, it's like a sheet of paper, you're looking at it edge-on, all you're seeing is the edge of the piece of paper. All right. So that's what it looks like, and it goes on to plus infinity and minus infinity. If we were to do sort of a 3D perspective of that, it kind of looks like a sheet of paper. But it's a sheet of paper that is infinite, so it goes off in all directions to infinity. How does the electric field point for this? Well, it's sort of similar to the cylinder when we look at it from a side view, because so the electric field points directly away from the cylinder, or from the plane, okay? And I should say that this infinite plane of charge has a uniform charge density, so there's not any like hot spots where there's more charge than other spots. If we look at this in 3 dimensions, it kind of looks like this. So you got electric field lines going up. And then we have also electric field lines going below. Like that. Okay. So what is our... Now, by the way, so let's talk about what's called sigma. So sigma is the charge per area. Okay. So coulombs per square meter. And sigma, yeah, so we can take, so for this infinite plane, it's a constant. So we can take both sides and we can multiply by the area and get that sigma times dA equals dq. Okay, so now we have to choose a Gaussian surface. And it turns out that we are going to use, again, a cylinder. But whereas the last time we had the cylinder is going side to side, now we're going to have the cylinder going up and down. Okay, so I'm going to draw it in the 3D view first. So it's going to be, actually I'll draw it in the 2D view first. So it's oriented up and down, and it actually passes through the surface. Okay, it has to pass through the surface because in order to use Gauss's law, we have to enclose charge. And then this one is a little bit tricky to draw. Do you mind if I'm going to draw this just a little bit bigger? So we have here's this. So I'm drawing this field line. Okay, and our Gaussian surface is like a cylinder that is like this. Have to okay, so that is this. So this is the part that is below the infinite plane. This is the part that's above. Okay. So I hope that makes sense. So Gauss's law says that the flux integral is equal to charge enclosed over epsilon naught. Now, again, a cylinder has 3 faces. There's, in this case, I'm going to call them top face, bottom face, middle face. Okay, so the left-hand side is going to be E top dot A top plus E bottom dot A bottom plus E middle dot A middle. Okay, now this is sort of the opposite of the last one, because if I look at the area of the top face, its area vector points up. So the area vector points up, and the electric field also points up. So here the angle is 0 for the top face. All right. For the bottom face, the area vector points down, and the electric field points down. So here on the bottom face, the angle is again 0. But if we look at the side face, the middle face I should say, the area vector points to the left or to the right. But the electric field points up and down. So that angle is 90 degrees. So the middle one has an angle of 90 degrees, and then the other two have an angle of 0 degrees. Okay? And if you recall, the cosine of 90 degrees is 0. So this one goes away. Here, we just get E top, area top, plus E bottom, area bottom. All right, just magnitude times magnitude, because cosine of 0 is 1. Now, by the symmetry of this Gaussian surface, it's a cylinder, so the area of the bottom face is the same as the area of the top face. Similarly, if we took the infinite plane and we flipped it upside down, it's still an infinite plane. So the electric field on the top is the same in size as the electric field on the bottom. Okay? So what we get is these two terms, both the electric field and the area are the same. So on the left-hand side, we just get 2EA. How much charge is enclosed? Well, we can see that here is the part of the Gaussian surface where we actually are enclosing the charge, because this is where it intersects with the infinite plane. Okay? And again, the cylinder maintains the same area throughout. So this area, it's like you're making a cookie almost, right? You're taking this cylinder and you're pushing it into the dough that's been rolled flat, okay? And so the area where it cuts out the infinite plane is right there, and it's the same area. So that means that the charge enclosed is sigma times the area. So the left or the right-hand side of Gauss's law is going to be sigma area over epsilon naught. The areas cancel. I divide by 2, and I can get that this is the electric field of the infinite plane. Okay? It's kind of interesting because it doesn't depend on how far away from the plane you are. So the electric field is constant no matter the distance from the infinite plane. The other thing that is a little bit more obvious is that if you increase the charge density, you get more electric field. That's pretty obvious. So that is my lesson for today, and I will see you in the Zoom room.